Recording is rolling. It is Thursday, January 29th. We're doing the spring oscillation lab. You guys have this table. Right, so I'll walk you guys through the steps of how to think about this, what we're doing, and then get you guys going on your way here. Okay. All right, thank you. So, um, so guys, everybody write your name on your table. Write your name. So when you eventually turn this in, I will know who to give the points to. Hey, guys, write your name. All right, so in front of you is this setup right here. You guys have a stand with a spring on it. You guys have a box of lab weights. Okay. All right. Okay, so I'll walk you guys through this table, how to think about what's going on. You guys got to collect some data, make some measurements here. Now, some of these columns are calculations. In fact, a couple of these columns put a little expression above, and I'll walk you guys through where that comes from. Okay, on the back of the page, do you guys see spaces for 4 graphs? 1, 2, 3, 4 graphs. Okay. Right, so more on that later. Guys, if you keep a pretty good pace today, you might finish this entire lab, including the 4 graphs today. Okay. If you don't quite finish the 4 graphs, then you can finish this tonight and turn this in tomorrow. You do that. Okay. And probably most importantly here is I want you guys to think deeply about the relationships among the variables, like what this all means, right, in terms of these relationships. Right? So there are so many labs today, give students, and sometimes you get the feeling students just kind of checking off the boxes, like, oh, what number goes in that box? Blah, blah, blah. There's like very narrow focus. But if you look big picture, like, what is the relationship between guys, what do you think would happen if you put a heavier and heavier mass on here and you pull it back and let it oscillate? It's the title here, spring oscillation. Would it take more time or less time? Like, what's that relationship? Right, so look at that. Okay. Oh, and then for my AP students, they have an assignment due Wednesday, but here, I'm just putting that in the recording just to mention that too. Right, you guys in front of me are honest right now. Otherwise, everything else is the same. Right, so let's look here. We got, right, so you could have different trials, 1, 2, 3, 4, 5, A, B, C, D, E, whatever. Okay. Next column, do you guys see mass? Treat this basically as the independent variable. I'll write IV above that column for independent variable. You guys have boxes of lab weights, so you could switch out whatever weight that you hang on here. Okay. And there's different things you're looking for. One of the big things you're looking for is, guys, what does K stand for a spring? Spring constant. Like how stiff is the spring, right? And there's different ways you can find it. So one way is you could hook on a lab weight and you could slowly lower it to rest until it comes to equilibrium rest point, right? And then you can measure that distance. You guys see where it says, actually, that's this one right here. Sorry. See where it says x equilibrium? Right. So give you guys another picture right here. Okay. So this is here. I hook this on right here, okay, and then I pull it down until it goes to rest, and then I take my hand away. Right now it's just at rest. Now, guys, do you see the distance I'm actually measuring? Guys, am I measuring the full length of the spring? No. Right. I'm only measuring relative to the unstretched length. You guys see that? Right. So this value here is like 0 stretch, and this is like however many centimeters that is. You guys see that? Okay. Now, there's another value you can get that's kind of interesting too. But if I go back to the beginning, so I'm going to hook this on right here, and then I just drop it. Is it going to overshoot the equilibrium and start oscillating like this? You guys think? Okay. And now I'm making the claim here. You can see it. I think we walked through this yesterday. That this maximum stretch value should be double of the equilibrium. And when you guys try this has been working out pretty well all day today. That should be pretty close to the case. So, for example, guys, if this was 5 centimeters, what do you think this should be pretty close to? Pretty close to 10. If you hammer between 8 and 12, then that's like right on track. Okay? This is for ideal springs. Okay? So can you guys actually take out the meter stick and record, like measure and record what's X max and X equilibrium? Can you guys do that? Now, from that, you have enough information at this point, to just see like what is X equilibrium to figure out what is the spring constant. And this goes back to Hooke's law. Do you guys remember Hooke's law? What does Hooke's law say for a spring? Like F equals Kx. Okay, so, guys, let's look at this equilibrium condition right here. Now, I'm covering up a little proof right here. Let's go through this. Okay? Guys, anytime you hear equilibrium in physics, you know the sum of what is equal to what? Yeah, sum of forces equals 0. So there's your framework. Okay, so sum of forces. Well, there are 2 forces. What are the 2 forces?
Gravity.
Yeah. Yeah, the weight's pulling down and the spring's pulling up. Now, the weight, call it mg, the spring force, here's Hooke's law, F equals Kx. Okay? And don't those have to subtract and equal 0? Okay. So if you knew 3 of these variables, you could solve for the 4. No, here I solve for how far it's going to stretch based on spring constant. Okay, could you just do a little algebra shuffle and solve for spring constant as a function of how much it stretches? Just switch the x and the k. Do you guys see it? And that's exactly where this is coming from. You guys see that? Exactly it. Okay, so pretty much this just one more shuffle there. Okay. All right, no, I might come back to this one, but let's go. Next column here. What's this about T10 and T1? What do you guys think those stand for? Yeah, oscillation time. So what if this is just hanging here at rest, and then you pull it and you let it go, and it starts it starts oscillating. You guys have some stopwatches. Can you measure how much time it takes? And what do you think would be a loose spring compared to a stiff spring? Okay, well, I got the spring scale versions. Right? Maybe this kind of a loose spring, this kind of stiff spring. Do you think a loose spring would be like and a stiff spring might be like you see that? Right. Okay, so however much time it takes. Now, I'm suggesting that you do 10 oscillations of about 10. Let's see how you count oscillations. Suppose you pull this down 2 centimeters and let it go. No, it goes all the way up and then comes back down. Is that one complete oscillation? Yeah. So if you count up 10 of those, so you let go. 0, 1, 2, 3, 4, 5. Right. By the time you get to 10, okay, suppose that number is like 7 seconds. If it takes 7 seconds to do 10 oscillations, how much time does it take to do 1 oscillation? How about point 7, right? You just divide by 10. 7 divided by 10 would be 0.7. Is it? Right. All right, so now what? Well, here, I'm telling you guys this formula is true. I guess the perspective of this lab is you're trying to get K from different perspectives. Right? So maybe you're sort of testing this out. Right? I'm handing this to you and you say, I wonder if this really matches the Hooke's law perspective. Right? This, of course, not Hooke's law. This is oscillating. Right? This will tell you time period as a function of the spring constant and also the mass that you attach to it. There's mass right there. Right? So, guys, let's do a little math and let's solve for K. Are you guys ready to do that? You guys ready? Okay. So I'm gonna write this down. So the time period oscillate once is 2 pi times the square root of m over k, where k is the spring constant, which let's say we're solving for that. Because you guys see that's what's coming up right here. What's the k from the perspective of it oscillating, right? Here's it oscillating, and let's solve for k, right? And so let's do some algebra. What's the first algebra step I should do? Divide by 2 pi? Yeah, you can divide everything by 2 pi. You can do that. And that gives you t over 2 pi is equal to root m over k. What's good next step? Yeah, square both sides. So see if I square both sides, it gets rid of the root. So that's t squared on 2 pi quantity squared is equal to m over k. Guys, can I do a little cross multiplication here? Or you do, actually, let's do reciprocal. Let's try that. So I can say k over m. So I just swap this out. Is 2 pi quantity squared divided by the time period squared. And finally, if I want to solve for k, can I just cross multiply the m now? Okay. So there's a few ways to get there through algebra. Okay. But regardless of what method you use exactly, if you do everything correctly, you should get that result at the bottom. Okay. All right, you guys good with all those steps? Okay. So this expression right here, 2 pi quantity squared times the mass that's oscillating divided by the time period squared, that is exactly that expression right there. You guys see that? So by the time you get the time period and you know what mass you attach to get there, can you guys just run that expression and get the k from the oscillating point of view? Okay. Now what you should see is that the Hooke's law perspective of k and the oscillating perspective of k should be fairly close to each other. Like if you run the Hooke's law and you get like 30 newtons per meter, you should get fairly close to 30 oscillation. Might not be exactly, might be somewhere between like 25 and 35, but it should be pretty close. Okay. Is that all right? Before I move on, let me ask you guys this. I didn't tell you guys how far to pull this. Right, so guys, suppose this is just hanging at equilibrium, right, and then I pull it down 1 centimeter, let go. You guys start. What if I pulled it down 2 centimeters? Would it take more time, less time, or the same time to oscillate? What if I pull it 3 centimeters? Is that more time, less time, or the same time? What does this say? Same time. Same time. Yeah, you guys got it. Because that's not part of the equation. Right? The only thing that's going to determine how much time it takes is whatever mass you attach and how stiff the spring is. It doesn't matter the amplitude. It doesn't matter how far you pull it. For that matter, it doesn't even matter the gravity field. Yeah, that's interesting too. Right. So, right, last couple columns here. These are manipulated axis columns. You guys see I'm telling you to square the time period and also take 2 pi quantity squared and times the mass. Okay, so these should just be numbers. I gave you the units. Okay, you guys do that, right? Okay. And what are we doing with that? Well, I'm gonna have you guys create these 4 graphs on the back, and I set them up for you guys to give you guys the titles and the axes. Ooh, looks like I didn't label units. Can you guys label units? That's probably a good idea. You guys can scale your axes and apply a bunch of points. Is it? Right. Now, I think I may have shown you guys this yesterday. I'll tell you guys what the answer is. So I'm sort of spoiling this. Okay. But this is what you should get. X max compared to X equilibrium. You guys remember that this box and this box are the same, except they're off by a factor of 2? Isn't that okay? Actually, X max we found you can find it on paper by doing conservation of energy. Okay, I think we walked through that yesterday. Okay. So I bet if you plot all these points for different masses, I bet you get a slope of 2 or very close to that. This looks like spring oscillation over here in the top right. Okay. Again, this is one way you can rearrange your variables so the slope of this line should be k. I mean, these dots should line up in a straight line, and the slope should represent k from an oscillating point of view. This down in the bottom left is basically Hooke's law. It's actually this is Hooke's law, wasn't it? It's like a perspective of Hooke's law. Okay? So the slope is also k. You guys remember f equals kx. Finally, this graph on the bottom right is a little different than the others because all the other ones, maybe you're hooking on different masses. Mass is kind of your independent variable. Get like a string of dots. They should all line up in a straight line. But this last one, what I want you guys to do instead is to pick one row, maybe like row number 3 or something, right? And then whatever the time period is, construct, well, basically this type graph right here. Okay. Guys, do you guys think that represents one time period, one full oscillation? So going back to my numbers from before, if it took 0.7 seconds to oscillate once, can you put 0.7 seconds right here? And then up to here, 2 oscillations would be like 1.4 seconds. 3 oscillations could be sometimes 2.1 seconds. Right? Okay, so you can figure that out, right? All right. All right, so you guys got the rest of class. Get all your data, make some calculations. Again, if you keep a pretty good pace, you might be able to even finish the graphs. If not, you can turn this in tomorrow.